In this video, I'm going to introduce the idea of linear dependence. Now, this is given by this definition. So if we have a set of vectors, v1, v2 up to vn, these are said to be linearly independent if the only solution to this equation, so here we've got a linear combination of v1, v2 up to vn, equals 0. If the only solution to this equation is where all of our alphas are equal to 0, then we say that these vectors are linearly independent. So if we have some non-zero solution to this, we say that these vectors are linearly dependent. So another way of thinking about it is a linearly dependent set of vectors is where some of the vectors can be expressed as linear combinations of the others. And to show whether a set of vectors is linearly independent, we need to solve a system of linear equations. So let's have a look at an example. So here we have three vectors. I'm going to show that these are linearly independent. So in other words, each of these vectors cannot be represented as a linear combination of the other two. Now we need to solve, if I just go back to this, so this is the key equation here. So alpha 1 times one of the vector plus alpha 2 times another, etc. So we need to solve this equation for alpha 1, alpha 2 and alpha 3. And we can write this as a matrix equation. So if you notice, this is the coefficient matrix. The columns of the coefficient matrix is each of our vectors. Okay, so we need to solve this equation. Many ways of solving a linear system. So I'm going to use Gauss-Jordan elimination. I've done a previous video on this, so I'm going to go through this quite quickly. So using our standard elementary row operations, I'm going to row reduce to reduce row echelon form. Okay, so I've gone over this has been quite quick. You can slow the video down to check this is correct. So at the end, this is reduced row echelon form. So we got 1 times alpha 1 is equal to 0, 1 times alpha 2 is equal to 0, and 1 times alpha 3 is equal to 0. So the only solution to this linear system is where we got all zeros. So if I just go back to the definition, okay, if the only solution to this is 0, then we have a linearly independent set of vectors. Okay, let's have a look at another example. This time we're using polynomials. So just because they're not vectors, we can still check whether these are linearly dependent. Okay, so I've got three polynomials. So I've got alpha 1 multiplied by my first polynomial, alpha 2 multiplied by our second, and alpha 3 multiplied by our third. So the next step is what I've done is I've factorised out in terms of the x squared, the x, and the constant term. So here we've got alpha 1 times x squared and alpha 2 times x squared. So I've got alpha 1 plus alpha 2. If I then take the x terms, I've got 2 alpha 1, 8 alpha 2, and 3 alpha 3. So that's where this bracket comes from. And finally the constant term. So I've got minus 1 lots of alpha 1, I've got 1 lots of alpha 2, and another 1 lot of alpha 3. Okay, so in order for the left hand side to be equal to 0, we need this bracket, the first bracket, to be equal to 0. So that gives us this equation here. We need the second bracket to be equal to 0, which gives us this equation. And we need the third bracket to be equal to 0, which gives us this equation. So here we have a linear system of equations that need solving. And this can be represented as this matrix equation. So again, using Gauss-Jordan elimination, so I'm going to go through the row operations. And in reduced row echelon form, we have this. Now here we have a row of all zeros. Okay, so we can't calculate what alpha 3 is. So alpha 3 is a free parameter, so let alpha 3 be equal to r, and then solve for alpha 2 and alpha 1. Now when r is non-zero, we can have solutions for alpha 1, alpha 2 and alpha 3. We have solutions, which means our alphas are non-zero. So we say that these polynomial functions are linearly dependent.